That's fine. Okay. Hello, everyone. I am Matthew Rahimi, and I'm coming from Havel, Belgium. So specifically Cozy Group. Cozy consists of more than 100 people, many PhD students. I'm a PhD student last year. I'm working mainly with Claudio Diaz on anonymous communication methods. And I'm really happy today to introduce some of my work that I've recently published here.
Sorry, could you speak up just a bit louder?
Okay.
Thank you.
Yeah, I think I'll try my best. Okay, so today I want to talk about latency aware routing and mixed network. And to make sure that we are on the same page, first I'm gonna briefly introduce why do we need to use anonymous communication network and why we need to basically reduce the latency in this network. So as you know, by default, if some communication advice want to connect to an internet, their communication will be secured using cryptographic protocol, right? But the fact that those points are communicating usually is not hidden from an, let's say, network adversary observing this. And it can raise some privacy issues. One of the typical way to address this for a client is to use Tor network. So a client can basically choose some relay from Tor network that we usually call them guard, middle, and exit, and can forward their messages through those relays. And with the assumption that internet service provider that lies between client and the guard relay, as well as the exit and the destination will not collide, we can kind of provide some sort of anonymity for this client. However, Tor network is not secure against an adversary to observe both ends of the network. So basically, the adversary can launch correlation attack and with high accuracy realize who communicated with whom. So no anonymity. To basically address this, we can use mixed network. So mixed network maybe had some problems because it has been introduced much in advance compared to Tor, but it had some like efficiency problem. But recently, NIM tried to adopt Lupix mixnets that can efficiently handle messages and packets. So it's a real thing that's happening, and it can be much effective in terms of providing anonymity compared to Tor network. So in more detail, a mixnet consists of some nodes that we call them mixed node. A mixed node is a network entity that will receive messages or traffic from different resources. And after receiving them, it will shuffle them and forward it to the next node in the network. And in this case, adversary observing this will not have any clue how to connect the input to the output, so kind of providing anonymity. If we then consider a network of such nodes that we usually layer them in different layers, we can construct a mixed network where a client can have higher anonymity by simply choosing one mixed node from each layer and then forwarding her traffic to those actually mixed nodes with the assumption of having like a stronger adversary who observe all the links in the network. But then, yeah, the client will just forward the message to the first node, then first node to the second and third. And in such case, even the adversary tries to corrupt some mixed node in the mixed network, as long as just one node in the message path operates honestly, then we can provide the anonymity for the client destination connection. Okay, so that's great. We had a privacy issue and we could effectively address it using mixed network. But mixed network provides the anonymity at the cost of high latency. The latency is high because essentially compared to the direct transmission, you need to send your packets through different intermediary nodes. They can be from different continents, so high link latency, and also each node will add some delay because of the shuffling purposes, right? So it can be detrimental in a sense that the client cannot adopt mixed network to have an anonymized like web browsing, for example. So today I'm gonna talk briefly about some works that we have done to provide low latency routing in mixed network. The first work is Lamix that recently presented in NTSS, and then two other work that one of them will be presented in CANS are some extension to Lamix. So in Lamix, we try to propose some node assignment to the mixed network and node selection that are kind of biased in order to have low latency routing, while making sure that we are not losing that much energy. So to start, we have different steps in learning. So at the very beginning, we realized that by default in mixednet, nodes will be assigned to the layer uniformly at random. And it can be problematic because in this case, we can have, for example, one layer, which is full of nodes from a specific location, for example, from Australia, and all the clients to have their packets going through that node. That can, for example, heighten the end-to-end latency. Instead, we propose that we cluster the nodes before assignment to the layers, and then we apply a diversification algorithm. I'm not going to this detail, but basically the result of using algorithm is that we have nodes from different location in each layer that can avoid the corner cases. Then in next step, we also realize that in baseline mixnets, basically a client will select each node from each layer in the form at random. And it can also contribute to high end-to-end latency because these intermediary nodes can be far from each other. We try to provide a strategic routing that will be controlled with parameter tau. So these parameter tau is for tuning the randomness in routing. When tau is low, then most of the routes would be through the nodes that are from the same cluster. Let's say they are close to each other. But when you increase the value of tau, the route would be with more randomness. And when tau is equal to 1, then we will meet the baseline case that everything is uniformly at random. Okay. And then as a result of applying this strategy routing, we also faced a problem. We found that there might be some mixed node that will receive high portion of traffic compared to other. And it can be problematic for two reasons. One adversary can, for example, propose some nodes to be mixed node in mixed network. And those nodes can have high capacity and take advantage of this issue. Or some nodes just don't have enough capacity and they will delay the packets. So queuing delay, again, high end latency. To avoid these cases, we provided two naive and greedy algorithms. The naive algorithm tried to simply balance the loads over the nodes, but greedy algorithm will do the same, but also take into account how the nodes are close to each other or they are far to each other, kind of maintaining the characteristic of routing. Okay. At the end, we also wanted to make sure that we are not sacrificing anonymity that much compared to the baseline because we want to have an anonymized network, right? So for that, we also introduced a metric that measure how predictable are the paths in a sense that an adversary who observes all the links will actually see a message going to a specific mixed address layer, and then he observes all the exit nodes, and then try to measure distribution of the loads, actually the distribution of this message over all the possible nodes at the last layer. And the entropy of this distribution kind of the notion of anonymity, because when we have the baseline routing, the entropy would be in highest level. For example, here it would be 2 because we have 4 mixers, right? But when we are trying to bias it, then we are reducing the entropy for anonymity, and we need to take care of that as well. Okay, then we actually performed many experiments. I'm just gonna show the main one, where we try to consider some real world data sets. We actually applied our strategy on those data sets and we tried to change the parameter tau. We saw that increasing the tau increases the latency as well as entropy or anonymity because we have more randomness in the network. And essentially, if you consider load balancing, your the latency and the entropy will be higher as well because load balancing needs to also add some randomness to redistribute the loads, right? But we found out around tau equals 0.6, we have a good trade-off. We can effectively reduce latency without losing much anonymity. And apart from that, we also have seen that if we have like a specific end-to-end latency that we need to meet, we can perfectly meet with our approach and providing higher anonymity compared to the baseline. Okay, so far I was talking about larynx. So larynx tries to make sure that the intermediary nodes are close to each other, right? But there might be cases like this example that client and destination themselves are very far from the mixer. And it can also cause high end latency. Then recently, I published a paper. I tried to manage the link delay between client and mixer as well with different approaches that, as you can see, we can have like uniform selection of the first node. We can have k alpha closeness that we will choose the low latency link with higher probability. We can have a linear programming to solve this to optimize the routing from client to mixnet, or we can exponentially prioritize the low latency links. And we have seen these approaches can have different costs in terms of implementation. We can have effective approach with efficient cost like exponential distribution or k alpha closeness. And at the same time, we try to measure the advantage of adversary. Here to be different, I don't go to the detail, but FC basically is the advantage that an adversary can gain. We found that it wouldn't be so advantageous for him. And also at the same time, we can reduce the latency effectively. And finally, I can very briefly introduce what I'm gonna talk next week in CANS. Basically, it's about the topology of the mixnet, that what would happen if we want to change the topology of the network, if we can have it still this kind of trade-offs. So typically in mixed network, we have layered network, but for layered network, to make sure that we are fairly assigning nodes to each layer, we need to basically run some cryptographic protocol like randomness generation that is publicly verifiable to have a fair assignment. And it's an additional cost that client need to pay. In some cases, clients doesn't need to pay this and they want to have a still efficient mixed network. And they are going after the three-root topology where each node can be connected to every other node. And in such scenario, I try to adopt the Larynx approach. And it turned out that we can have a strategic routing, we can have load balancing. It can be more challenging, right? Because every node is connected to other nodes, so you need to be more careful when you are load balancing the network, but still it's achievable. And you will lose less in terms of entropy because you have more connection. And turned out that this kind of network can be more even beneficial in terms of having low latency routing. So yeah, I think I was quite fast. So in conclusion, I would like to mention that we have a privacy issue on internet. We need to address it. One way is to use Tor, but Tor is not actually secure I mean, in the face of the adversary of everything in the network. And we can use mixed network, but it can increase the end-to-end latency. But using Larynx or other words that I have mentioned can effectively address it. And I hope that one day we can implement it in real network. Thank you so much for listening. You can have access to the papers, to the implementation, also this type of slides, and also my webpage release QR code. Thank you so much.
Thank you.
I'm quite interested in what application group you perceive as being advantaged by this latency management at least, or latency reduction that are running on the mixed nets and so forth?
Yeah, actually, I think so far, NIM is adopted, for example, for Telegram and WhatsApp, if I'm not mistaken. But the problem that they had was that the latency was really high. Like, for example, it would take like 2-3 seconds just to send a message and be received by the receiver. So using our approach can make it really fast. Or for example, let's say, I think Tor is quite good for web browsing, but Mixnet still is not well adopted for web browsing. So why? Because of this high latency. If our work is adopted for Mixnet, I'm sure that it can be so beneficial, for example, for web browsing. And other, let's say, latency sensitive applications.
Fair enough. Not being a security expert, I think I might have misunderstood, but there's got to be a trade-off. So what did you lose?
So you want to use mixed network to have anonymity, right? But the anonymity, like, it's like a trade-off between anonymity and latency. If you want it to have faster, for example, you can just ignore using mixnet, just directly send your packets. So you have zero anonymity, but it's the fastest possible way. You can use Tor. It would be a bit slow, but you have some sort of anonymity. But if you want to have higher anonymity, so you need to like spend more on in terms of latency, right? So if you want to lower the latency, definitely you will lose some in anonymity. For example, I mean, in one of the experiments, we found out you will use like 2 bits of anonymity. Should be here, I think. Yeah, 2 bits of anonymity in the green graph, but you will reduce the latency by like 78%, something like that. Yeah.
I was under the impression that with like NIM style networks, most of the end-to-end latency was due to the artificial latency injected at each mix node rather than the network latency of the packets actually traveling over the internet. So did I understand correctly that you're only trying to optimize the part of the packets traveling over the internet part of the latency and not changing the latency at the nodes themselves?
Yeah, actually we have 2 different strategies. The experiment that I've shown in this slide is about the time that you don't want to touch the mixing process at each node, right? You just want to optimize the link delay. So you can definitely use our approach. But another time you might say, okay, I don't care what you want to do, but I just want to have like for end-to-end latency, the limit of 200 milliseconds. In this kind of cases, we also show that how you can use our approach to manage both the, also, you know, change both the link delays and also the mixing process. So it can work for both ways.
So does that mean you would put some information on the packet saying, hello, I'm a low latency packet because I'm part of an audio conversation or something. Please apply low mixing latency to this particular packet, or how do you how does the mix know what latency to apply?
So I am client. I want to I know which application for which application I'm using the mixnet, and in advance I'm gonna measure that. Okay, with respect to the data that I got from the network, okay, I want to, for this application, I need to have this 13 latency to meet, right? The latency should be less than this time. So I'm gonna check that how I can manage it, how much mixing delay I should apply for my packet, because I am the one who will choose the mixing delay at the end. So it's all in my, not mix node. I'm gonna choose this much mixing delay, and I'm gonna choose also the mix node. I can definitely manage how to use. I don't know if I.
Right, yes, but my question was, how does the mix node know how much delay the client wants to add to the packet?
Yeah, actually, it has incorporated to the packets.
It's part of the packet structure.
Yes, yes.
Okay.
Yeah, that's true.
But is that something that would then leak information to an adversary observing the packets? Because, like, generally, I think like the 6-packet format, for example, tries to make the entire packet look like an indistinguishable from random string. Whereas if you now have a field in there that indicates that this is a latency indicator, would that perhaps not be uniform random anymore then?
No, actually, it's totally random. Basically, you put everything. Like for example, I choose let's say the first node, and I have a message for that node, right? Along that message, I will basically concatenate the latency, and then I'm gonna encrypt that, right? So it's all everything is encrypted, and then the node after receiving that will like detach that part, and then decrypt it, detach it, and then send the remaining to the next node, right? It's still is encrypted. There is nothing, no information about that mixing. Okay, yeah. Yeah.
It's a little bit unrelated, but the QR code you provided within the scan.
You need to select a plan
Yeah.
to keep the QR code alive.
Okay.
And it's for some QR ransomware.
Yeah, maybe just, yeah.
If you want to remove the redirection.
Yeah, I probably I'm gonna redo it. I'm gonna just maybe send an email later.
And use a single QR code per slide because you can't really select them.
Sure, that's fair.
One QR code to a web page where you have all those things.
Yeah, I mean, I have provided the slide maybe 1 or 2 weeks ago, and I never thought that it's gonna expire or, yeah, sorry for that.
Question from Nick online.
Hi, yeah, I had a question following on the question two questions ago, which is can one of the intermediate hops disregard the latency preference and introduce its own timing delay in order, if it's colluding, say, with a passive adversary, in order to introduce a timing side channel that can give signal to other parts of the network as to the trajectory of this packet and where it's ending up and between kind of whom it's being sent.
Yeah, that's a great question. So basically, we have different type of mixing. I didn't go to in that details. Usually for mixed node, we have like a verifiable shuffle algorithm. They kind of need to provide some proof, and this proof will be checked to make sure that, for example, this packet is shuffled properly, and it has been sent to the, for example, next node. And specifically for Need Network, I think very recently a paper came out and they explained how it works. It basically works based on VRF, verifiable random function, that's each node kind of will provide some proof that I actually apply the delay. So it's kind of like, it can be like avoided by applying this kind of workflow. But they prove that, yeah, they have done their work correctly. But they can definitely, for dropping the packet, for mixing delay, they cannot do anything, but they might, for example, drop the packet. But the question that what will happen if they drop, will they be able to kind of distinguish who communicated with whom? Basically, no, because everything is encrypted and they don't know at which position, for example, this packet is received. So yeah, I mean, nothing would happen, but the client needs to again send the packet from the beginning to make sure that the destination will receive it. But then, yeah, it can be also, those nodes also will be going to the detection because then the client can complain at some point that my packet even did not sent to the destination, were not sent to the destination, for example, and kind of it can be detected. But yeah, I mean, that's a fair question, but it can be avoided. I hope that that was it.
Thank you.
Welcome.
Any other questions, or should we move on? I think Eric, you had something to share today, didn't you?